In this project, we look at building a fully functioning end-to-end project using neural networks and mobile technology. This will give us an intuition for the application of machine learning, mobile technology, and single-board computers. However, I'm not an expert, and this is not a tutorial. And as with all aspects of life, you must risk assess your own activities. That said, I hope you're able to gain an intuition into this very exciting area of applied machine learning and go on to do your own experiments. So, let's gain an intuition from machine learning by replicating the ability of a smartwatch to automatically detect activities such as walking, running, and unicycling. Let's look at what we need to replicate a smartwatch. We need a movement to classify, something the person can hold that translates their movement into a digital signal, a neural network trained to classify that movement with a confidence level, then finally, a means to display the prediction of what the movement is. We then need to make this work for all of the movements we're interested in classifying. Right, let's have a look at the technology to do this. To replicate the electronics in a smartwatch, we use the Arduino Nano. It can easily be held in the hand and powered by a simple USB charger pack. The Nano also has an accelerometer that can detect movement as a stream of digital signals, and a Cortex M4 processor that is capable of running simple neural networks, and finally, it has Bluetooth capability, making it very mobile for activity monitoring. Okay, so what software do we need to make this work? Firstly, we need a way to collect our training data. So, we write a program on the Nano that can send accelerometer readings over Bluetooth to another program that can collect that data. We can then use this data later as training data for our neural network. We create two options for this: a Python program that can run on our desktop for simple experiments, and a mobile application written in Flutter that will allow us to collect training data on the move. We now need to train a neural network with the data that we have collected. For this, we need a Python program that can take the training data for all of our activities, unicycling, walking, and running, then break it up, label it, and use it to train the neural network. Now we have a trained neural network, we can use it to predict movement. The first option is that we run our existing data collection program on the Nano and send movements over Bluetooth to a new Python predictor program to do classification. In this case, the Nano is just acting as a data collector, but is not yet making local predictions with the trained neural network. This is a good first step to ensure the network is properly trained. The second option uses the ability of the Nano to run neural networks on its own local processor. This requires a few steps to make it work. The trained neural network is first converted into a special binary form that is then incorporated inside a new predictor program that is loaded onto the Nano. This program then takes the readings from the onboard accelerometer and makes predictions in real time over Bluetooth. These predictions can be picked up by yet another Python program or by the Flutter application that we have written for our mobile device. To make things simpler, we first experiment with predicting hand movements. The process is exactly the same, but we can perfect things at our desk before we start running, walking, and cycling around the neighborhood. The three hand movements we will predict are stationary, up, down, and circular, which we will do while holding the Nano. Before we look in detail at the programs, let's do a quick demo of the Nano sending real-time predictions to our mobile app. Here we will use the Samsung tablet to run our mobile app, and the Nano with the activity predictor program that executes the neural network on its onboard CPU. Let's go to the tablet and open up the mobile app we wrote. When it opens, it scans for all Bluetooth devices. The ones it recognizes by name as our Nano device, it lists in the top section so we can interact with them. When we press connect, the app establishes a link over Bluetooth with the Nano. This causes the Nano to start making real-time predictions and sending them over the Bluetooth link to the application. If you watch the app prediction, it will correctly show the movement of the hand. However, it will do this with a slight lag as it is sampling a rolling window of 20 points in time. In a moment, we will highlight the erroneous up-down prediction in red. This is where the window effect causes a bad prediction as we transition from circle to stationary. So we now have the elements of our simulated smartwatch. A device that we can hold or wear on the move, the ability for that device to track movement and classify it with an onboard neural network, and a mobile device that shows those predictions in real time. Perhaps a bit less convenient than the smartwatch, but a prototype we can now experiment with and learn from. Now we have an overview of the process and have seen the final outcome. Let's do a deep dive of how we did this. If you're interested, the GitHub project with all the code is linked in the description. So, let's do a quick tour of the code. Here we are in the GitHub repository. Let's do a quick tour before we demo the individual components. As we've seen so far, there are three main areas. The Python utilities for collecting the training data, training the neural network, and running simple experiments. The Arduino programs for sourcing the accelerometer readings as training data and running the local neural network as a predictor, and the mobile application for collecting training data and making predictions on the move. Let's have a quick look at the Python utilities. Before you can run any of these Python programs, you'll need to establish the same environment. Here's how to do that using Anaconda and an environment file saved in the project. The first utility listens to the Arduino Nano over Bluetooth and saves the accelerometer readings as training data. The second utility takes that training data and then builds and trains a neural network. It can also export the trained neural network as C++ code for use with the Arduino Nano. This utility listens to an Arduino Nano over Bluetooth and classifies the accelerometer readings in real time. This utility listens to an Arduino Nano running in predictor mode and prints the predictions being sent by Bluetooth from the Arduino Nano on the screen. This utility converts the JSON file to C++ such that it can be used with the Arduino Nano. And finally, we have the checkpoint folder where versions of the neural network are saved while it's training. Let's have a look at the Arduino programs. The first program allows the Arduino to collect accelerometer readings and transmit them over Bluetooth to be saved remotely as training data. The second program allows the Arduino to take accelerometer readings and classify them with a trained neural network loaded locally and then send the prediction over Bluetooth to be displayed remotely. Finally, let's have a quick look at the mobile application. The mobile application is written in Flutter, which will work on iOS or Android devices. However, at this point, it's only been tested on Android. The application finds the Nano devices through shared configuration held in the conf.json file. The application can connect to an Arduino running the collector program or the display program. When connected to an Arduino running the collector, the program will allow you to choose a movement type to record. It will then save all of the remote accelerometer readings from the Arduino Nano as a local file that you can use for training later. When a Nano is connected to while running the display program, it will start to make movement predictions with its local neural network. It will then send those over Bluetooth, which this application will display on screen. Now we've had the general overview, let's look in detail at collecting training data. Before we can collect training data, we have to write a program for the Arduino Nano to listen to the accelerometer, package it up, and send it over Bluetooth such that it can be stored remotely. Here, we see our data collection program for the Arduino Nano loaded in Arduino Studio, which is how we edit, manage, and load these programs to the Nano. Let's have a quick tour of the project. Here's the main program that we'll come back to in a moment. We have a class that manages accelerometer readings, a class that contains all of the shared configuration as JSON, and a class that allows us to use the onboard LED to indicate status. Back in the main program, The first thing we do is import the Bluetooth module and then the accelerometer module. Then before we get going, we have to extract the configuration from JSON so that we can configure and advertise the Nano as a Bluetooth device. If all goes well, we signal that by cycling the LED status. And then in the main program, we loop waiting for a Bluetooth connection. And then as soon as there's a Bluetooth connection, we collect and send accelerometer readings until the other end disconnects. All that's left to do now is upload the program to the Nano so we can use it. The first thing we do is ensure that the Nano is plugged into a USB port and connected to. And then we upload the program as follows. We'll speed this up to save time. Now the Nano is programmed, we can unplug it from the computer and power it up using the USB charger pack. This will allow us to make the hand gestures freely while collecting the training data. Let's use the Python data collection program to record one set of training data for a circular hand movement. If we type -h, the program will list a full set of options. The minimum we can specify is the time to record for and the movement type being recorded. Here we are specifying how to record 10 seconds of a circular hand movement. Once the program has connected, we see the accelerometer readings corresponding to the hand movement being received over Bluetooth and printed on the screen. When done, the training data is automatically saved in the data folder in a file with a number on the end to make it unique. If we look in the data folder, we will see all of the training files that we have created in this way for all of the movement types. Here, we can see the latest file that we have just created. Let's open the file in Google Sheets and see what was captured. There were 50 points captured in 10 seconds of recording. This is because our data collection program on the Nano is configured to sample 5 times per second. This sampling rate is our first hyperparameter. We'll revisit hyperparameters later when we talk about training the neural network. If we create a simple chart, we can get a better sense of the data. If we want our predictor to work not only for one person but anyone, we must think about our training data. Our neural network can be no better than the data we train it on. This is a very central theme of machine learning and AI. If our data is poor, incomplete or biased, then the neural network will not perform as well as we need it to, or worse still, its predictions may mislead us. Poor data could be that we don't have enough data, or that the data is not representative. This could be if we mislabel data and mistakenly save an up-down training set as a circle training set. Incomplete data could be that we don't have data that covers all cases. Here, if we don't collect any data on up-down hand movements, then the neural network can never learn to predict up-down. For bias in data, the size and shape of the circle made by our hand can vary, as well as the speed our hand is moving. So good data would ensure that we capture as many combinations of size, shape and speed as possible. We could do this by collecting data from as many people as we can, otherwise the neural network would have a bias to predicting how our hand moved rather than the general case. Now we have a varied set of well-labeled training data. Let's see how we create and train a neural network. Once the network is trained, we will also see how we export it such that it can be loaded onto the Nano. Before getting into the details, let's see what the main Python training program does. If we run it with the -h option, we can see all of the capabilities it supports. We'll hear more of the options later, but to train the network, we only need the training data location and the neural network model type to build. Both of these have defaults, so if you run it with no arguments, it will look for the data in a local directory called data, and it will create and train the one-dimensional CNN model. Tensor-Flow Lite on the Nano only supports some neural network types covered by full TensorFlow. The CNN, the convolutional neural network, is one of the supported models, which is why we use it here. If we run the training program with default arguments, it first loads the TensorFlow environment and then creates and displays the model details. Here we see the model that was created in the code. We will revisit this in detail a little bit later. Next, it loads all of the training data and starts the process of training the model. This involves running many training iterations over the data until the model is able to predict with reasonable confidence the action being performed. We speed this up, as even with a GPU it takes a while. After training, the program shows a graph that represents the network's learning. The blue lines show the error and the orange lines show the validation error. In both cases, we see a rapid drop in the error as the network learns, i.e., its ability to predict correctly is increasing as it makes fewer errors. The lines in the top right are just a zoomed-in view of the lines below, so we can see in more detail as the learning errors become very small. Let's look at how we transform the training data and design a network to learn about it in the way we have just seen. We need to transform our data so it can be passed to a neural network. So, after some experimentation, we choose to break the time series of data up into blocks of 20 points. Then, with our chosen sampling rate of 5 points per second, it makes each sample block about 4 seconds long. 20 is another hyperparameter, where a hyperparameter is selected with trial and error rather than with rigorous process. We will see more hyperparameters later, and it is hyperparameters that make the science part of data science more of an art. We now have fixed size samples of 3 by 20 data points that we can randomly shuffle and use to train a network. Once trained, the network will be able to take any similar slice of data from the accelerometer that it has never seen before and predict with a confidence level the type of movement it came from. Let's open the main Python program for the training and have a look. First we parse and load the arguments that drive the program. We then load our shared configuration, and then we create the activity model class that's going to drive the process. First thing we do is load the training data. If we're going to use saved weights, we load from a checkpoint, which will allow us to do experiments with a pre-trained model. Otherwise, we train the model from scratch. Finally, we run simple tests to see how well the model trained. Let's have a look in more detail at the activity model where all the hard work is. The first thing we do is create the model, and here we see the support for the 3 model types, the default CNN model that we use and 2 additional models that you can experiment with. If we look at the code for the CNN model, we'll see the network being defined that we're using for all of our experiments. We first define the shape of the input data to match the 20 by 3 blocks we have transformed our accelerometer readings into. Following this is the TensorFlow Keras code that defines a simple CNN model suited to the classification of our data. This is a very simple neural network, both because the classification problem is simple, but also because the power of the Nano CPU is limited. There are many hardwired decisions in this code. Again, these are hyperparameters, and these are the subject of more experimentation to find ideal values. You can experiment with the other 2 models here to see what happens when you change the network architecture and hyperparameters. However, be aware, not all the configurations you come up with will be suited to TensorFlow Lite on the Nano. If we jump back to the main activity model, we can see the next thing to do is load the training data. And here's the code that iterates over all of the training data that we created, so the model can be trained from it. If we jump back again, we can have a look at the code that trains the model. The part that does this is the fit function. It iterates over the training data and makes adjustments to the internal parameters of the neural network to minimize errors and maximize prediction reliability. Lastly, we have the test function. This takes a set of data that was not used for training, so it has not been seen by the network before. It then uses this data to run an independent test to see how well the model performs. It prints this out as a confusion matrix and also displays the graph we saw earlier. Now we have a trained neural network, we can test it. We do this by running the Python predict program on the computer and feeding it accelerometer readings by connecting over Bluetooth to the Nano. We're going to run the Python test program that we'll look for and then connect to the Arduino over Bluetooth. Once the connection is established, the test program will make real-time predictions of the movement using the trained neural network. The program uses Tensor-Flow to create and load a saved version of the trained neural network. Once it's loaded, the program starts collecting accelerometer readings from the Nano. As highlighted in blue, we need to collect at least 20 readings before we can start making predictions. If you watch the predictions highlighted in green, they should agree with the movements of the hand in the insert video. The red highlight indicates an incorrect prediction. This is because the hand is switching from one movement type to another, so the observation window overlaps two movement types. This is a hyperparameter trade-off for 20 sampling points. Less points means less indications of the movement, and more points means a slower response to change. Now, let's see how we can get the trained neural network onto the Nano so it can run onboard predictions on its own CPU. Let's recap. We take our training data and use the Python training program to create and train a neural network. The code is configured such that during training, we keep saving down the best version of the network we have seen so far as a checkpoint file. So, when we are done training, the last checkpoint file saved will represent the best version of the network. This version is the version we need to use to make predictions. So, it is a neural network with weights from this checkpoint file that we need to get onto the Nano. We do this by using the Python program to load the checkpoint file into a neural network, and then asking the program to export that neural network in a binary form understood by the Nano. To get this binary form of the model onto the Nano, we have to embed it in a C++ file that we can copy onto the Arduino Studio project and then upload to the Nano. Once the Nano predict program has been updated with this version of the network, the Nano will be able to make local predictions by feeding the accelerometer readings directly to the onboard neural network and then sending predictions out over Bluetooth. These predictions can then be read by either a Python test program or by our Flutter app. We can run through this in the project. First, we check there are no old versions of the exported neural network. We then run the Python program that can regenerate the exported version of the network, and we do that with the help option. Option L loads the checkpoint from the last successful training. Option T causes the network to be converted to a binary Tensor-Flow Lite form and then exported by the program as a .cpp and .h file. These can be copied to the Arduino Studio project and uploaded to the Nano. We can see these files in our chosen editor. So, we open up the .cpp file and copy the entire contents. Then, we go to the Android Studio project and replace the previous .cpp file. Now we have the new model ready to upload and run on the Nano. We press the load button, and as soon as it is uploaded, we can test with the Python command line or the Flutter app. We have seen both of these already, so we won't repeat here. We've now seen the entire project lifecycle. Using the Nano to collect accelerometer training data over Bluetooth to both Python and our Flutter app. Training the neural network with Python. testing the trained neural network with Python, then exporting the model so it can be run as Tensor-Flow Lite on the Nano, and finally, testing the neural network on Nano to both Python and our Flutter app. So, we'll finish here with a quick tour of the Flutter app. We'll do a quick review of the app before we look at it in Android Studio. When we open the app, it scans for all Bluetooth devices. Those it recognizes by configured name as Nano devices, it shows in the top section. The app keeps scanning Bluetooth, so we see the two types of Nano device appear as we power them up from their USB charger packs. If we connect to the data collector, we can select movement types and start and stop recording as needed. The app saves these files locally, so when you connect your mobile device to your computer, you can copy those files onto that computer and use them as training data. If we connect to the activity predictor, we see the live predictions being made by the Nano. So, as we move the Nano around, the predictions change as we've already seen. Okay, so let's have a look at the Android Studio project. Android Studio allows you to create projects for different mobile device platforms, some of which we can see here. For this project, we have used one of the mobile and tablet standard layouts. This generates the general machinery and framework so that we can focus just on the application specifics. So, let's have an overview of the code that we've created. Main.dart is the entry point where we find the function that builds the home page we see when we start the application. Here in the initialization function, we see the creation of the three key elements: the class that manages the Bluetooth connectivity, the class that manages the predictor view, and finally, the class that manages the data collection view. The Bluetooth class is a utility wrapper on the Flutter Blue open source package. We create some high-level utility functions that make it easier to find, connect, and interact with the Nano as a Bluetooth agent. The predictor class is very simple. It just reads the predictions being sent over Bluetooth from the Nano so they can be displayed on screen. The data collector class both listens to the accelerometer readings from the Nano over Bluetooth and also arranges to save them on the mobile device under a file with an appropriate name to the training data being collected. For each one of the classes, there is a corresponding section of code that manages the view seen on the application screen. The main view that finds and lists the Bluetooth devices available to be interacted with, the predictor view that shows the real-time movement being sent from the Nano device while it is predicting movement types, the collector view that allows training data types to be selected, and then the saving of the accelerometer readings coming from the Nano. So, we've now seen all aspects of the project and the process, so let's make a few tweaks that will allow us to collect data on and predict the movement types of running, unicycling, and resting. The key thing to note is that we're not going to change the program code. We're just going to record new data for running, unicycling, and resting, and then retrain the same neural network to predict these new movements. This is the key difference with AI and machine learning over traditional programming. In traditional programming, the knowledge is fixed in the code. In machine learning, it is encoded within the neural network, where the neural network is flexible enough to learn about new or similar activity just by training on additional data. And finally, we put the whole thing together. We copy the data we collected on our mobile setup for resting, running, and unicycling onto our computer. The model is then retrained using the new data and the labels. And after it's trained, we verified that the model has learned and that it is able to predict with reasonable accuracy by examining the final validation error and the confusion matrix. Now, so we can go mobile with our prediction, we export the new model in Tensor-Flow Lite format and copy it to the Nano. Finally, we can go back outside and verify that the newly trained Nano can predict the activities in the field. It turns out that the predictions are less stable than with the hand movements, so some tuning of the hyperparameters and the observation window is probably needed. It also proves that unicycling while holding a Nano and a tablet is not such a great idea.